So, now we are starting our discussion on curves on surfaces. So, in the first unit we discussed curves in space, in the second and third we discussed surfaces, and in the last stage we are in a position to discuss curves which are drawn over a surface. So, if you have a surface in a space whose parametric equation is r equal to r of u1 u2, and you have drawn a curve C over it, surface is sigma, and if you want to write its equation will be given by u1 equal to u1 s, u2 equal to u2 s, that is u1 u2 both if they become function of a single parameter s, which I choose it to be a natural parameter, then this is the equation of the curve, and any position vector on the curve, position vector of any point on C is given by r equal to r of u1, which is a function of s, u2 which is also a function of s, and therefore, r becomes a function of s. Okay. Now, if you remember, we can talk of the curvature of the curve. So, if I forget the surface right now and look at the curvature of the curve, so we know that if t and n denote the unit tangent of the curve C and n denotes the principal normal, if t and n denote the unit tangent and principal normal, of C, then we know that t dash, the derivative of t with respect to s, which you can also write as r double dash, is equal to the curvature of the curve into n. This is something that we already know. What I am going to emphasize today is that this vector I will be calling as k bar. Okay. So, k n is in fact a vector along principal normal, which I will be calling as k bar, the curvature vector. Just wait. So, this vector I will be calling as the curvature vector. Okay. Now, see some other things. Now, this curvature vector will be along the principal normal of the curve C. So, what I will do in order to see where it is, introduce a new vector. Introduce a new vector. U, which I write as n cross t. Now, you can see in order to define u, I have taken help of two vectors n and t, where n is related to the surface and t is related to the curve, okay, and you know where they are. So, it is easy to see from here that u is perpendicular to n, as well as, and u is also perpendicular to t. So, now these two informations are there, then you can guess where this vector u is. From the first relation, it follows that u lies in the tangent plane. Anything which is perpendicular to n would lie in the tangent plane of the surface. So, what follows from here is that it lies in the tangent plane of the surface. of the surface sigma. Okay. And this only tells you that it is perpendicular to T. T also lies on the surface, because any tangent, any curve that lies in the over the surface, its tangent would lie in the tangent plane. So, this T lies in the tangent plane and u also lies in the tangent plane, but it is perpendicular to T. So, u is perpendicular to T. So, nothing else, all right. So, if I draw a normal over here to the surface, then T is like this is the unit tangent of the curve, and then you have to look at the tangent plane. There will be some tangent plane also here. So, your u will be this vector. This u is perpendicular to T as well as it is perpendicular to n, but it lies in the tangent plane. So, now think of n. U is think of and where will it be? Think of the normal n with a v, the surface, where do you see it, where it will be? Okay. Now, n, we know n is a vector perpendicular to T. This we know. That n is a vector which is perpendicular to T. It lies in the osculating plane. Osculating plane we are not going to deal with today. So, you will consider a vector which is perpendicular to T. Now, what are those vectors which are perpendicular to T? In fact, there will be infinitely many vectors which are perpendicular to a given vector. If I give you a vector in a space, there will be infinitely many vectors which are perpendicular to the given vector. But if I give you a vector in a plane, then there will be only one or two, the other one is opposite direction, but in space there are infinitely many. In fact, there will be a whole plane perpendicular to T. So, there is a whole plane which is perpendicular to T. So, n will be lying in that plane. Is it right? And can you guess what will be that plane which is perpendicular to T? If you look at the figure, you can easily tell me that T is perpendicular to a plane which is generated by u and n. Is it right? So, it follows that n lies in the plane of u and n. Both of them are perpendicular to each other. So, they are linearly independent and therefore, they will be generating a plane. And since your vector k bar is along n, it will also lie in the plane of k and n. Therefore, the curvature vector k, I will call it the curvature vector. K lies in the plane of u and n. So, k must be written as a linear combination of u and n. The difference in our discussion is that earlier we used to regard curvature as a scalar quantity. For the first time, we are thinking of a curvature vector. Once you realize what curvature vector is, it is nothing but k times n. It has certain magnitude which we still call curvature, but this fellow is called curvature vector. And therefore, therefore, hence K can be written as a linear combination of U and N. In fact, I have decomposed K into two parts, one along U and the other along N, or also I can rewrite down this as Kg bar plus Kn bar. Okay. So, that is Kg bar is the resolved part of K along along the surface. I mean, it is tangential to the surface, and Kn bar is the resolved part of K along the normal capital N. Okay. But this N I am making as a in the suffix of K. So, one should be careful about the notation as well. And this scalar quantity, moreover, the magnitude of Kg bar, magnitude of Kg bar is how much? Is simply Kg, that is Kg equal to Kg bar dot U. U is a unit vector, that is why you say that the dot product will be its magnitude. Why U is a unit vector? Because N is a unit vector, T is a unit vector, and both of them are perpendicular to each other. So, the cross product of two unit vectors which are perpendicular to each other will always be unit. And the magnitude of this Kg bar, and this I will be calling as geodesic curvature. Okay. And Kn, the magnitude of the normal curvature vector will be Kn bar dot, and this I will call as the normal curvature. So, the curvature vector has got two components, one along N, one along U. So, the component of the curvature vector along N is called the normal curvature, and the component of K bar along U is called the geodesic curvature vector. Okay. So, this is the definition of geodesic curvature and normal curvature. You can call Kg bar as the geodesic curvature vector, and Kn bar one can call as the normal curvature vector. All right. Let me see anything else I have to do. All right. There are some. Okay. There is another relation. You can call it as a immediate corollary of these relations, and that is the Kg is given by as a scalar triple product of n r1 r not r1 r dash r dash r double dash. Okay. Okay, so this Kg by definition I can prove it So, by definition Kg is given by Kg bar dot vector u, and Kg bar I can write down as, if you look at this relation number 1, I can write down Kg bar as vector k bar minus vector kn bar dot u. So, this becomes k bar dot u. Kn dot u will be 0 because Kn is a vector along capital N and u is perpendicular to n. So, this dot product will be 0. So, you have this. So, k bar is if you remember is r double dash, okay. And what is u? U is what? N cross T, or you can also write down r double dash dot n cross T, I can write down as r dash. So, this is the scalar triple product of these 3 vectors, where you can cyclically permute them, and it is same as n r dash r double dash. So, this was a straightforward result for Kg. All right. Okay. Next, we have some expressions. Expression for Kg. Expression for the geodesic curvature Kg. So, you know Kg is given by okay. Yes, we know that k is r double dash, vector k bar is r double dash, and r dash, if you remember what is r dash, this is number 1, r dash is T, and if you see this is dr over ds, that I can write down del r over del ui into dui over ds. Okay. I is a dummy index over here. So, this becomes Ri into dui over ds. This is r dash. R double dash will be what? R double dash will be d by ds of this. So, d by ds of Ri into dui over ds. So, if you want to differentiate this product, so you will differentiate with respect to uj. So, that will become Rij into dui over ds into duj over ds, okay, plus Ri as it is into d2ui upon ds square. Okay. And this Rij, we have studied Gauss Gauss formula. So, from the Gauss formula, I can write down Rij as gamma Kij, this is a small k, into Rk plus Bij into n. This is Rij by Gauss formula. Dui over ds, duj over ds, plus I can write down, I can change the name of this dummy index and call it Rk. So, okay. So, d2 uk upon ds square r k. Now, r k I can take common from here and here. So, that will give me k I j into du I over ds du j over ds plus d2 u k upon ds square into r k plus you have component of b I j. B I j into du I over ds du j over ds into capital N bar. This is your r dash, r double dash, sorry, and it is also equal to k by relation number 1, k bar in fact. So, if you look closely, the vector k bar is written as a linear combination of r k's and n. In other words, this part is tangential to the surface, whereas this part is normal to the surface. So, you can say that this part is k g bar and the other one is k n bar. Okay. All right. So, k g bar is this quantity and this quantity is k n bar. So, k g bar, that is k g bar equal to gamma k I j du I over ds du j over ds plus d2 u k upon ds square r k plus, and then and the other fellow is k n bar. K n bar is b I j du I over ds du j over ds into n. Now, you can see what will be k g, the geodesic vector. So, geodesic curvature k g is equal to k g bar dot u. You may call this as number 1 first and this as second. So, first let me deal with the first relation. So, that will become k I j into du I over ds du j over ds, okay, plus d2 u k upon ds square r k dot u. So, k is a dummy index. So, there is a summation over k. There is a summation over k. So, that is understood. Let us call this relation as number 1. So, when you will take the sum, you will be getting r1 dot u and r2 dot u over here. So, let us see what will be r1 dot u and r2 dot u. So, consider r1 dot u first. R1 dot u means R1 dot, what is u? U is n cross t and t is r dash, and r dash is what? R dash I have written here in the r dash I had written in the beginning, it is r I du I over ds. Here it is, I am sorry, it is here. So, it should be r1 dot n cross. So, this is, if you expand this summation, it will be r1 into du1 over ds plus r2 into du2 over ds. This is r dash. So, now when you will take this cross product, in fact this will give you a scalar triple product. So, in the first case when you will take this term together with n and R1 will repeat in the scalar triple product. So, in a scalar triple product, when the two vectors are collinear, it becomes 0. So, you will be getting here only the last term will give you R1 dot n cross R2 into du2 over ds. So, that becomes R1 dot I can make it minus times R2 cross dot and cross can be interchanged. So, this will be minus times R1 cross R2 dot n. du2 over ds is still there. So, this becomes minus R1 cross R2 dot n is also R1 cross R2 upon under root g into du2 over ds. So, this is R1 cross R2 into R1 cross R2 means mod of R1 cross R2 square, that is simply g. So, you have g upon under root g into du2 over ds, minus is there. So, this becomes simply minus under root g into du2 over ds. So, this is the value of R1 dot u. Similarly, I can find out the value of R2 dot u. Similarly, R2 dot u you can check up by yourself is under root g, this time it is positive, into du1 over ds. So, these are relation number 2 and 3. Now, substituting the values of R1 dot u and R2 dot u into number 1, substituting from 2 and 3 into 1. Into 1. You will be getting kg equal to 1 I j into dui over ds duj over ds plus d2 uk upon ds square. R1 dot u is minus under root g. So, under root g I can take common. Under root g I can take common. So, this is minus times du2 over ds and plus R2 dot u is here. So, plus this is minus and this is plus. Okay. So, this will be 2 I j dui over ds duj over ds plus d2 uk upon ds square into du1 over ds. Okay. So, this is the expression for geodesic curvature, and this can be written in the form of a determinant du1 over ds du2 over ds in the first row. Du1 over ds is to be multiplied by this. So, this will come over here and du2 over ds is multiplied by this. So, 1 I j gamma 1 I j dui over ds into duj over ds plus d2 u1 upon ds square, and du1 over ds is multiplied by this. So, this is 2 I j dui over ds duj over ds plus d2 u2 upon ds square. So, this becomes the formula for the geodesic curvature. Okay. Now, there are some special cases for geodesic curvature. The immediate thing that comes to our mind, what will be geodesic curvature of some of the known curves. For example, the one of the basic known curve over a surface are the parametric curves. So, let us see what will be the geodesic curvature of parametric curves. So, geodesic curvature of parametric curves. So, the answer to this is geodesic curvature to parametric curves are these. I do not know where did I write down. Okay, I did not write anyway. Okay, well, anyway, Kg1, we can work it out. It becomes, we can work it out. Okay. Yes. So, geodesic curvature for u, we know that for u1 curve. Let me take u1 curve first, u1 curves. So, for u1 curves what happens is, for u1 curves u2 is constant and therefore, du2 over ds will become 0. Okay. And if you take du2 over ds equal to 0 over here, then it will be simply, I will call it the geodesic curvature of u1 curve as Kg1. So, from this formula you may call it formula star. So, from the formula star we have this will be 2 I j into dui over ds duj over ds plus d2 u2 upon ds square multiplied by root g. Okay. And okay, du1 over ds is there. So, du2 is 0 and therefore, second order derivative will also be 0. So, the second term is 0 over here, and now let me expand it under root g. When you will expand this summation over here, I and j both are dummy indices. So, I will put 1 1 into du1 over ds whole square. When you will put one of the index as 2, du2 over ds will occur and that will be 0. So, only this term will be non-zero multiplied by du1 over ds. So, this is du1 over ds whole cube. So, now what will be du1 over ds? If you want to simplify, you know that ds square is equal to g11 into du1 square plus g12 du1 du2 plus G22 du2 square. This is the first fundamental form on a surface. Now, if you are computing the first fundamental form along u1 curve, so du2 is 0, therefore, middle term will go as well as the last term will go. So, du1 upon ds whole square is equal to 1 upon g11, and if you want to remove square, it is 1 upon under root g. So, du1 over ds is 1 upon root g1. Substitute this value over here, you will be getting under root g times 211 into 1 upon g11 whole to the power g11 lower whole to the power 3 by 2. So, you get under root g upon g11 whole to the power 3 by 2 multiplied by 211. This is the geodesic curvature of u1 curve. And similarly, you can work out geodesic curvature of u2. Similarly, one can work out we can find geodesic curvature of u2 curves. Okay. All right, and then yes, if the parametric curves are orthogonal, then you can see what will happen to this expression. Yes, that can also be seen. Okay, what will be the geodesic curvature of the parametric curves if they are orthogonal? So, if parametric curves are orthogonal, then you will be getting one more condition, then G12 is 0. And now what I will be doing, I will be writing down in place of G under root G, then Kg1 by from the last formula will become under root G11 into G22, G12 will become 0, and this is G11 whole to the power 3 by 2. I can simplify 211 also, Gauss formula. For 211 we know how to compute 211. Christoffel symbol 211 is by definition 1 upon 2 where G22 only, G21 will be 0. So, this is delta GIM means 212. So, this is will be 0 plus delta GJM once again G12 is this will be 0 minus delta G11 Ij upon del U2. So, this become half G22 will become 1 upon G22 when G12 is 0. So, you get minus times delta G11 upon delta U2. So, substitute this value also. So, minus I will put over here half okay, G22 into delta G11 upon del U2. So, you can settle what are the powers. So, minus half G113 by 2 and this is G half. So, this half goes off only G11, G22 half and G22. So, this will become under root G22 down, okay, and that is delta G11 upon delta U2, okay. Am I right? Now, this can be further written as 1 upon under root G22 into del of log G11 under root okay, because you have half minus half 1 upon under root, you can check it up. Check it up whether I have written it correct. Okay. So, I hope this is correct, and similarly you can compute Kg2. We can compute Kg2 when parametric curves are orthogonal. Parametric curves are orthogonal. Similar expression you will be getting there. You have to work on the same lines. I stop at this point. We will continue tomorrow.